In part 3 of finding the moment of inertia, we're going to calculate the moment of inertia for some uniform objects, taking advantage of tables. In a lot of cases, if you have a uniform object, by that I mean an object made of one type of material that's been uniformly distributed throughout the material, then it's what's called a homogeneous object. And that object, if it has a fairly common shape, will have actually been solved by somebody using calculus, and they will have placed the answer to that into a table. And so you don't have to know calculus to work the problem. You can use the tables or figures such as 8-21 on page 208 of Physics 6th edition by Giancoli, or in some other textbook if you're using a different text. Now, how big your table is depends a lot on the type of problems you're doing. For instance, a practicing engineer will have a fairly large table of moments of inertia and center of masses that they keep around. But in almost all these tables, these axes will have had to have been solved, or the moment of inertias will have been solved, about an axis where there's some sort of symmetry, such as if it's in the middle of the object. This is usually the center of mass axis. So they're somewhat limited, but there's a trick called the parallel axis theorem which can be used to extend your table to non-center mass axis. So let's look at this using this technique to solve a problem. So you have this problem. There's a uniform solid sphere here in red, and there's a hoop that right here in black, and they're rotating about a vertical axis shown through here around like this at some omega, and they want me to find the moment of inertia of this system of two objects. Well, this doesn't turn out to be very difficult because both of these objects are inside Giancoli's table. For instance, for the sphere, he tells us that it's 2/5 the mass of the sphere times the radius of the sphere squared. And we know the mass of the sphere in our problem is 4 kilograms, and the radius of the sphere is 0.5 meters. And he tells us that for a hoop, that it's the mass of the hoop times the radius of the hoop squared, and we know the mass of the hoop is 2.5 kilograms, and the radius of the hoop is 0.3 meters. In fact, every one of these uniform shape looks like the mass of the object times some length squared, and then some factor in front. The hoop's the biggest. It's got 1. A cylinder is a half. So I like to say a pulley or cylinder is half a hoop. It's not half a hoop, but that's a way to remember it. A sphere is 40% of a hoop. Now, to solve this, we just solve for the individual elements, and then we add them up, just like you would add up mass in a linear problem. So the hoop, 2.5 kilograms, 0.3 meters. We have to square that. Then we have to put all that together with our calculator, and I get 0.225 kilogram meter squared. And for the sphere, 2/5, 4 kilograms, 0.5 meters squared. Plug all that in, I get 0.4 kilogram meter squared. Find the total. I total is equal to I hoop plus I sphere, and that's 0.625 kilogram meter squared. Easy. No calculus, no fuss, no muss, because it's in our table and it's on the center mass axis. So if they're in your table in Giancoli, life's pretty simple to handle these objects. In fact, it's easier than handling small little objects, small little balls that you have to add up. It should be noted a couple things here. All of these, I told you, is like some sort of gamma mr squared. Some number from 0 less than or equal to gamma less than or equal to 1. 1 for a hoop, 0, object is not rotating. 1/2 for a cylinder, 2/5 for a sphere. And by the way, that should be a hoop, not a hope. And for instance, 1/12 ml squared for a bar. But it's an ml squared. For bar or rod. Alright, so they all have that shape. Now, it depends on how you want to look at that. Physicists will look at this as if it changed the mass. And I'll show you why that's helpful when we do the Newton's rotation problems a little later on for like blocks sliding down an inclined plane. It makes the mass of a pulley or such, if it's a cylinder, look like it's half the mass. If it's a hoop, it looks like it's a full mass. If it's a sphere, it'll look like it's 40% of the mass of the object. So we look at it like that. Engineers often want to consider comparing the rotation of one object to another. And so they'll rewrite this as follows. They'll rewrite this as I equal m, and they'll either use a k squared or mg squared. And they call this the radius of gyration. And what they mean by that is that if you have a sphere, and it has 2/5 mr squared, if they were to turn that into a hoop, what radius of a hoop would they need to have exactly the same difficulty to rotate as the sphere? And what they find is that they need to have mg squared equal to m times 2/5, 2/5, I was right, 2/5 r squared. So you can cancel the m, and g is the square root of 2/5 of the r. So it's effectively like a smaller hoop, and it's smaller by the factor of the square root of 2/5. And you can punch that into a calculator and find out what that number is. And about 63% of the radius. So it makes it look like it's a hoop, but it's a hoop of radius 63%. And why do they do this? Because they have a feel for a hoop and they want to do comparisons. That's why they do it. Now let me tell you how to make your table even bigger. The parallel axis theorem. Neat little theorem. If you happen to know the moment of inertia for a center of mass for some rigid body, like a hoop or cylinder, which you will if you have your table. So if you know that, and you want to know it for some other axis that's parallel to the first axis, you can find it by adding the product of the object's mass times the square of the distance between the new axis and the center mass to the object's moment of inertia. That may sound complicated, but it's not. Let me write the formula and then I'll show you. Take your center mass axis off your table, take the total mass of the object and multiply by h squared. And here's what h is. You take, let's say, a cylinder, and you know the moment of inertia about that axis, center mass. But you want to know if you were to rotate it about some other axis, say over here. This distance between these two axes that are parallel is h. So take the value you have here, 1/2 mr squared, and add the total m times this distance squared, and that's the axis for trying to rotate it about this new, that's the moment of inertia for trying to rotate it about this new axis. It's easy. All you got to do is calculate this one term with algebra and add it. And it makes your table, in essence, infinitely big because you can solve it for that axis, this axis, this axis, this axis, this axis, this axis, an axis, say right in here. It doesn't matter where the axis is, as long as it's parallel. It won't work for that axis. The axis has to be parallel to the first. That's why they call it the parallel axis theorem. Now let me show you an example of something that you've already got in your table so you can compare. We know if we had a rod and its length was L, that if you were to do it right here in the center, so this is minus L over 2, and this would be, say, L over 2. If you were to do it right about there, the moment of inertia rotating about the center is 1/12 mL squared. That's in figure 8-21 of Giancoli. He also has the answer to my problem, which is, what is it to rotate about an axis here? Well, I'll call that the prime. It's equal to the center mass plus the mass of the rod times h squared. Now what's h? H is this distance. Well, that's L over 2, half the rod. So I prime is 1/12 mL squared plus m times L over 2 squared. That means the moment of inertia is 1/12 mL squared plus mL squared over 4. Now I need to find a common denominator for those. mL squared, I have 1/12. 1/4 is 3/12. So that means mL squared, 1 plus 3 is 4/12. But 4/12 is 1/3. And that value is also in Giancoli. Notice something else useful about this. The center of mass will always be less than anything else because you're going to add a positive number to it. The easiest axis to rotate, as I said previously in another video, is about the center mass axis. Now sometimes you don't want it to be easy to rotate, like on a door. You want the door to close and close firmly, so we put the hinge at the end. But that makes the moment of inertia, the hinge, bigger. If you want to make it easy to rotate, put it in the middle. People can push it from either side, but it makes a more complicated door. Very, very heavy doors that may have to be moved, or if a lot of people have to get in, they'll have rotating doors with the shaft down the center. All right, that finishes our discussion of moments of inertia.